Hello dear students, today we will discuss hybridization. Chemist Linus Pauling first developed the hybridization theory in 1931 in order to explain the structure of a simple molecule such as methane using atomic orbitals. For his scientific work, he was awarded Nobel Prize in Chemistry in 1954. It is the process of mixing and recasting of atomic orbitals of same atom with slightly different energies to form equal number of new orbital of equal energy, maximum symmetry and orientation in space. Some important points about hybridization. First, only those orbitals which have approximately equal energies and belong to the same atom or ion can undergo hybridization. Number of hybrid orbital produced is equal to number of atomic orbitals mixed. Third, it is not necessary that all the half-filled orbital must participate in hybridization. Even completely filled orbital with slightly different energies can also participate. Fourth, hybridization never takes place in isolated atom, but it occurs only at the time of bond formation. Fifth, the type of hybridization indicates the geometry of molecule. One can tell the shape of molecule by knowing the kind of hybridization involved in it. Sixth, the bigger lobe of hybrid orbital always has positive sign, while the smaller lobe on the opposite side has negative sign. Now we discuss sp hybridization for beryllium hydride molecule. It is the process of mixing and recasting of one s and one p orbital of same atom with nearly equal energy to form two sp hybridized orbitals having equivalent energy, maximum symmetry and definite orientation in a space. It has a bond angle of 180 with linear geometry which can be explained on the basis of hybridization. So first we write the ground state of beryllium 1s2 2s2, then in excited state one electron from 2s shifts to 2p orbital, resulting in the formation of sp hybridized orbital. So how they are hybridized? So 1s and 1p, they undergo hybridization resulting in the formation of sp hybridized orbital. So this is the sp hybridized orbital of beryllium, which is further overlap with two hydrogen atom, resulting in the formation of beryllium hydride having linear structure, bond angle of 180. Now we discuss sp hybridization of carbon atomic orbitals. So sp means uh, in sp hybridization there are two sp hybrid orbitals which are arranged linearly, and there are two unhybridized p orbital which are perpendicular to the linear orbitals. So we take the example of ethine C2H2. In ethylene molecule, there are two carbon hydrogen sigma bonds, one carbon carbon sigma bond, and two carbon carbon pi bonds. So these are the pi bonds, these are sigma sigma, and sigma bond is also present between carbon carbon atoms. Now we discuss sp2 hybridization by taking the example of boron trifluoride molecule. It is the process of mixing and recasting of 1s and 2p orbitals of same atoms with nearly equal energy to form 3 sp2 hybridized orbitals having equivalent energy, maximum symmetry, and definite orientation in space. It has bond angle of 120 with trigonal planar geometry. Now take boron in the ground state, 1s2, 2s2, 2p1. In exciter state, one electron promotes from s to p. We get 3 sp2 hybridized orbitals, 1s, 2p undergo hybridization resulting in the formation of sp2 hybridized orbitals. So it has trigonal planar geometry and bond angle of 120 . Now sp2 hybridization of carbon atomic orbital. We take the example of ethylene C2H4. So in ethylene, it possesses 4 carbon hydrogen sigma bonds, one carbon carbon sigma bond, and one carbon carbon pi bonds. So from here we can also predict its structure. C double bond C. So you represent 4 hydrogens at the bond angle of 120 . So either you can draw the structure. From here you can predict the hybridization structure, or if we knowing the hybridization structures, we can predict the geometry of the molecule. Next we have sp3 hybridization for methane molecule. It is the process of mixing and recasting of 1s and 3p orbitals of same atom with nearly equal energy to form 4 sp3 hybridized orbitals having equivalent energy, maximum symmetry, and definite orientation in the space. It has bond angle of 109.28 with tetrahedron geometry, which can be explained on the basis of hybridization. First we write again carbon in ground state, then promote s electron into the p, resulting in the formation of 4 sp3 hybridized orbital. So carbon the 4 sigma bonds around it with 4 hydrogen atom, and we get tetrahedral geometry. C H H H H. So this is the intermixing of 1s and 3p orbital. They undergo hybridization, resulting in the formation of sp3 hybridized orbital of carbon atom.